Hello, my name is TJ Ternage, and I'm a meteorologist at the National Weather Service in Grand Rapids, Michigan. The purpose of this presentation is to describe the concept of Bayesian thinking and how its use of probabilistic thinking applies to weather forecasting as well as all other aspects of life where uncertainty is involved. My motivation for putting together this presentation is based on an increased emphasis on probabilistic forecasting across the entire weather enterprise, including the National Weather Service. Probabilistic forecasts require us to think probabilistically, and this is where Bayesian thinking, sometimes referred to as Bayesian inference, comes in handy. Unfortunately, as things currently stand, training of this type is currently in limited supply. That is why I want to start a conversation right now about how we might make probabilistic thinking, or thinking in bets as Annie Duke would say, a central part of how we think. First, a disclaimer. I am not an expert in probability and statistics, cognitive psychology, game theory, or any of the other topics I'll be brushing past in this video. All I've done is read some books and made a few connections along the way with how we operate as forecasters. So yes, you can say the imposter syndrome is alive and well here. In fact, there's a good chance you'll even hear me say I'm not sure at least once. All of this reminds me of one of my favorite Dave Barry quotes that I will share with you here. My hope is that what I present here prompts discussion and debate, and as I said before, gets the conversation started. This presentation borrows very heavily from the books listed here. In fact, many of the examples I give are directly from at least one of the books. I will make an effort to give attribution as appropriate as we go through this presentation. To introduce the concept of Bayesian thinking, I will start with a simple example. Imagine there are two taxicab companies, one red and one blue. We learned that a taxicab is responsible for a hit and run in the middle of the night. A witness claims it was a red cab. The witness is tested for their reliability in making the distinction between red and blue cabs, and it's determined they're 80% accurate with discerning between the two. So, what's the probability it actually was a red cab? You probably guessed 80%, and that is a good guess given what we currently know. But now what if I tell you that only 15% of the cabs in the city are red and the rest are blue? What's the probability now? Many people would still say there's an 80% chance it's a red cab. However, the real answer is around 41%. That is because before we had an eyewitness, there was only a 15% chance of a red cab being involved, and the eyewitness is less than 100% accurate. In the first scenario, your initial and reasonable assumption probably was that there was an equal number of red cabs and blue cabs. In other words, your prior probability of the cab being red was 50% instead of 15%. So now we're ready to talk about the three ingredients of Bayesian thinking. The first is prior probability, which you were introduced to in the previous cab scenarios. Ingredient 2 is hypothesis testing. The third ingredient is posterior probability, which, as we will see, is used to update expectations in the form of a new prior probability. I know this all sounds very technical, but it will make more sense as we go through some examples. Already in our day-to-day existence, we revise expectations as new information becomes available. Having a better understanding of the process should help us to minimize the cognitive biases that often arise. We already touched upon prior probabilities with our cab examples. Even though we don't always put an exact percentage on it, we constantly make first guesses that something will or will not occur. I've listed some examples here, and I encourage you to practice by estimating prior probabilities for events in actual percentages during your day-to-day existence. This is what Annie Duke advocates in her book, Thinking in Bets. Now, let's circle back to the thunderstorm climatology example you see here. We understand that experts can recognize when there's potential for rare events, but before anyone can anticipate the extreme environments associated with rare events, they first have to know what normal environments should look like. The good news with prior probability is that it really can start with a simple first guess. You may not get to the best answer as quickly as an expert does, since they usually start with better informed first guesses, but you should get there eventually too, just so long as you don't start with a 0 or 100% probability. More on that later. Hypothesis testing is related to looking at model guidance. In our hit-and-run cab example, the eyewitness was like a forecast model that predicts an 80% chance of something happening. It's the same general concept as using a probability of exceedance in an ensemble prediction system, just like I show in the example here. That's the easier part. However, we also need to estimate the probability that something will not happen or will happen due to other circumstances. A shortcut for estimating this is to take the difference between 100% and the probability of the event. So if a model gives a 54% chance of something occurring, then we will say there's a 46% chance that it won't happen. Although this shortcut works for the most part, I should stress that estimating null hypothesis probabilities can be far more complicated and impactful. To illustrate an example of complexity, suppose a forecast model ends up being right for the wrong reasons, as the saying goes. In theory, that possibility should be accounted for in the null hypothesis probability, but in practice we typically can't recognize it, let alone quantify it, until after the event, and then at that point we're subject to hindsight bias. The final step is posterior probability, where we revise expectations based on new data for a future event or based on a past outcome. I give examples here that follow up on the prior probability examples I gave earlier. Note the friend example I give here. Although posterior probabilities typically are used to update prior probabilities, they can also be used to update your hypothesis probabilities as well. Bayesian thinking can be nicely summarized by this equation. We have discussed the ingredients shown here as x, y, and z. Now it's just a matter of plugging your estimates into the equation to get an updated posterior probability. There's something else about this equation that is not immediately obvious. What happens if you set your prior probability to 0% or to 100%? The answer is your posterior probability will never budge from the 0 or 100% you started with. In other words, this is the exact opposite of thinking in bets. So now we even have an equation for being stubborn. Let's go back to the taxicab example to see how this works. Recall that 15% of cabs are red. An eyewitness says a red cab was responsible for the hit and run, and the eyewitness is 80% accurate with what they report. Now you can see why I said earlier there is only a 41% chance of the offending cab being red. Now let's take a scenario that's much closer to home. We will see how probability of precipitation, or POP, ought to evolve with new information, which in this case would be newer model runs. Let's say you inherit a forecast with a 40% POP and the latest model guidance gives 60%. In the National Weather Service operations, this would typically adjust the forecast to 60%. But let's look at it from a Bayesian perspective. We will first put the numbers in our table. Then we will run the calculations to discover a better answer at this stage would be 50%. Let's say, for the sake of argument, and much to the chagrin of our forecast collaborators, we make our new prior probability 50% instead of the model advertised 60%. And what do you know, the newest model guidance continues to give us a 60% POP. If we run the numbers on that, we get an answer of 60%, and we are in harmony with our neighbors once again. Okay, you know the drill by now. We'll take the latest posterior probability of 60% and make that our new prior probability. And guess what? For the third time in a row, the model gives a 60% POP. Guess we're locked in now, right? Wrong. We now have a POP of roughly 70%. Alrighty then, I'm taking one on the chin again for Bayes and going with a 70% prior probability. And again, I've alienated myself from my forecasting colleagues at other offices. If the latest model run gives us a 60% POP for the fourth time in a row, my POP can only go down now, right? Wrong again. Our new posterior probability has climbed to 78%. So what does this mean for us in the forecast business? First, we must recognize how we tend to treat the most recent model run as correct until proven otherwise. This also is a classic example of recency bias. We're constrained to this because it's the easiest way to have the same starting point and play nice in collaborated forecasts. But playing nice also involves compromise, which often will trend probabilities towards 50%, which is the central tendency bias. Therefore, we should be aware of when Bayes' theorem gives probabilities much greater or less than the official forecast so that we can calibrate our messaging and biases accordingly. Here's an example of how we might calibrate. Try to remember a time when several model runs in a row gave you an 80% or greater chance of rain. Can you think of a single time that it ended up not raining? I sure can't. Well, thanks to Bayes' theorem, we now have an explanation along with the justification to be highly assertive in our external messaging to partners and to others when these situations present themselves. I will now conclude with the final and dramatic example that shows how Bayes' theorem can work even in a black swan type of event. That is, an event that is so rare and so outside the realm of normal experience that predicting it is extremely difficult. At 8:46 a.m. on September 11, 2001, a Boeing 767 wide-body commercial jet crashed into the North Tower of the World Trade Center. It's easy to look back now and say this was a terrorist act, but that's hindsight bias at work. Let's run this scenario through Bayes' theorem. For variable x, the concept of deliberately crashing airliners into buildings was nearly unthinkable, but not zero probability either. For y, we will assume that the success rate, so to speak, of a building being hit given a terrorist attack is 100%. Variable z is interesting because passenger planes have accidentally hit New York skyscrapers before. One occurrence was in 1945 and it happened again in 1946. So, if we approximate 25,000 days between these incidents and 9/11 in 2001, we get about 1 chance in 12,500 of another accident occurring on any given day. Putting all of this together gives a posterior probability of 38%, which helps explain the confusion at the time. Then, less than 20 minutes after the North Tower was struck, another commercial jet hit the South Tower. At this point, people knew well beyond any reasonable doubt that these were not accidents. And Bayes' theorem helps to explain why. Our new prior probability has jumped to 38%. If we keep the other numbers the same, we now have a nearly 100% chance of these incidents being deliberate. Thank you for sitting through this video, which I hope will foster discussion about thinking probabilistically in our professions as well as other aspects of our lives.